All right, we'll go ahead and get started. So, welcome to Chem, Gen Chem 1100. So, my name is Walter Gavlik. I'll be your instructor this semester. And just to tell you a little bit about myself, so I received my bachelor's and master's degrees in chemistry from St. Louis University, and then my PhD in analytical chemistry from University of Massachusetts. When I got out of grad school, I went into industry, worked there for 30 years, and then retired a few years ago and have been teaching at Webster since then. So glad to be here. Thanks for taking the class. I'm glad you're here too, whether you're in person or online. Can someone who's online tell me if you can hear me okay?
Can hear you good.
I'm sorry, what was that? Could you hear okay?
Yep, we can hear you fine.
Okay, great, thank you. Maybe you can hear it better than I can hear you, so that's okay. The important thing is you're able to hear me. I did teach the class earlier this morning. The way this is set up, it is a little difficult to hear questions coming from the Zoom people. So, you know, if you have a question, please ask, but I'll try and stop a few times during the course of the lecture to give you a chance to ask questions if you do have them. People in the room, obviously, just raise your hand if you have a question and let me know. A few like housekeeping things. One is I will take attendance for the first couple weeks to make sure I have the right people in the right sections and people know where they're at and all that. So we'll do that in a moment. Everything associated with the class, the slides, the assignments, things like that will be posted in Canvas. I'm trying to do recording of the 2 lectures so I can at least post one of them on a YouTube channel we'll have. Once I'm certain that's working, I'll let you know. And then I'll give you the address of that. So in case, you know, it's Friday night, you're looking for something fun to do, you load up the old Professor Gavlik lecture and there you go, you know. Makes that social distancing a little more tolerable. And so hopefully you can get that and that'll work okay, and then have that in case you do have questions. But the slides are out there. They're under the files section folder in the Canvas, and in there in the files there'll be a lecture folder within that. There's also the assignments in that. Please check your Webster email. I do send stuff out through that. I won't send it to your personal email. It'll go to your Webster email, so check that for just if something comes up or whatever. Let's see, what else? The class. Hopefully you've had a chance to look at the syllabus. That has the outline of kind of the pace we're going to try and go to. We'll just have to see if that's the pace we wind up doing. It may be a little slower, maybe a little faster. We'll just see. There's some of these unknowns of just like if the technology messes up or something like that, that could change the schedule. But the syllabus is the target of what we're trying to do. If you look on there, this week we're going to look at chapter 1, and then would have a quiz next Monday. Okay, that's kind of the goal. We'll see if we do that or if that gets pushed back to Wednesday. But right now that's the plan. The quizzes and tests will all be online. Okay. And so that's one of the changes. Normally, you know, to have a quiz or test, you'd all sit here and pass out pieces of paper, you do the quiz and you hand it in. That's not going to be that practical given that a large portion of the class will be online. So to manage that, the quizzes and tests will all be online. That means 2 things. One, it means it's open book. So in other words, you know, you want to look something up on the internet, you want to look in your textbook, whatever, you can do that. I'm not going to police that at all. But so that you can't just look everything up, time will be a factor on the quizzes and tests. So the way the test will be set up, there will be a certain time of day that you can take it, a window there. And then once you click on the exam or the quiz, a timer starts. And based on the number of questions and how long I think it should take you to do the test, if you kind of know this stuff, you'll have that amount of time. And when that time's up, it's up. So what that means is, if you say, gosh, I'm never going to have to study, I'm going to Google every one of these questions, you won't get through the test. And so if you do know the stuff and you say, oh, okay, I know that, it'd be kind of like if I asked you, where do you live? You could tell me that right away. It wouldn't take you any time at all. But if I asked you where I live, you'd say, well, I don't know that. I have to go get some information about you and Google it and do it. That may take me 15 minutes to figure that out. That's the kind of idea, is that for people who've studied and understand the material, they'll be able to have plenty of time to get the test done or the quiz done and do fine. If you don't know the material and you're looking everything up, then you're going to run out of time. So that's a little bit different than how the tests normally are. That time becomes a little more important on these. The other thing I'll mention is you're on the honor system for doing these tests and quizzes on your own. I don't want you getting together a group and doing the tests all together. If you do that and I find out about it, that'll be considered cheating and then be dealt with appropriately for cheating. So the idea is the tests and quizzes are tried to assess what each of you have learned and and how you're comprehending and learning the material. So we want to keep it at that. Any questions about any of that? Okay. The other thing about the quizzes and tests is you get to drop one quiz and you get to drop one test. You can't drop the final exam, but you can drop one quiz and one test. So in other words, so if you do bad on one, but you do pretty good on all the rest, that one won't negatively impact you. If you miss the quiz or miss the test, that counts as your drop, okay? And so, so make an effort to take the quizzes and tests so that you preserve that drop for being just one that you didn't do as well on, okay? So, any questions about any of that stuff? All right.
I have a question
Sure.
about that. So if you do sports or something, you're gonna miss that test date. Are we allowed to do a test a different date, or can we do it earlier?
So okay, so two things I'll say. One is if you have sports or something like that, you need to talk to me ahead of time. I guess I was under the impression that all sports were canceled for this semester. Is that correct?
Well, my sport doesn't start until late this fall, so I was just asking ahead of time.
Yeah. No, if this was a normal semester and you're a student who is involved in some sports activity or some other type school activity like that, then what you would do is you would talk to me ahead of time about it and we'd work out whatever that is. So when I'm talking about missing it, it's more for people who didn't show up for whatever reason. Maybe they weren't ready for the test, so they said, I'm just not going to take it, I'll take it later, or something like that. But I think the sports thing is less of an issue this semester because of just the canceling of the games and stuff for the semester.
Okay, thank you.
Okay, thanks. Any other questions? Okay, so I'm going to go ahead and take roll. I'm going to start with the people who are in the room. And so if I call your name, please raise your hand, because if you just answer, I have no idea who it is. Okay, Anna Barton. Tony Sebahar. Did I say that right? Sebuhar, okay. So there's a very good chance I will mispronounce your name. If I do, I apologize and just correct me. Scott Detweiler. Okay. Nadia Dowry. Okay. Evan Ellis. Okay. Amber Estes Brooks. Okay. Aaron Gallagher. Peyton Hanser. No Peyton, okay. Irma Jakubovic. Kaylin Kearney. And Isabel Llewellyn. Okay. All right. Now I'm going to ask the people who said they wanted to be only remote. Jessica Brock. Jessica, are you there?
Yeah.
Yes, okay. Heather Jones.
Here.
Thank you. Jalala Muhammad.
Here.
Okay. Cody Neal.
Here.
Destiny Shelton. Destiny, are you there? Edith Scampo.
Edis? Yeah.
Edis, okay, thank you. All right. So those were the students who said they wanted to be remote only. Now I'm going to read the students who today are remote and on Wednesday will be joining me here. Okay, Bolani Akanyemi. I'm sure I didn't get that right.
Yeah, it's Bolanle Akiemi.
Okay, thank you. Sorry about that. Bethany Lancaster.
Here.
Marissa Lanzati.
Here.
Nicholas Lozano. Nicholas, are you there? Mia Maddock.
I'm here.
Cheryl Moore. Cheryl, are you there? Devin Patterson.
Here. Here.
Okay, thank you.
Oh, okay.
Nathan Rivera.
Here.
Devin Schulstad.
Here.
Katrina Soltzwish.
Here.
Okay. Is there anybody on the line who I did not call? Okay, great. Thank you. Now, let's actually do what we're here for. So, yes.
How do you feel about technology like laptops and stuff? Taking notes.
Can you bring them?
Yeah, like can I take notes on it, or would you prefer us like paper? You don't like the technology?
You do whatever you want. If you like paper, that's fine. If you want to type away, that's fine. It's whatever you're comfortable with. So what we're going to do today is we're going to start chapter 1. And as you can see, we're going to talk about matter, energy, measurement. So this is kind of the start of things. What you'll find in this Gen Chem class is if you took a lot of chemistry in high school, for instance, if you took AP chemistry or something, a lot of this you may be familiar with. That's great. If you never had a chemistry class in high school at all, that's okay too. You're going to learn it in this class. So either way, no matter where you are on that spectrum, we'll go through the material. If you have any questions, please ask me. If during the course of the semester you start getting confused or struggling or something, please talk to me about it, okay? What I don't want people to do is I don't want you to sit here and be confused or lost or something, and then 6 weeks into the semester after we've had tests and quizzes and things like that, then come to me. Come to me in the beginning, because then we can work together to kind of get you on the right track. And so the other thing I'll say is that there will be some homework problems assigned. I don't collect the homework, but it really is beneficial for you to kind of do those, because the tests and quizzes are going to be based on the homework. They're going to be based on the homework, based on the material I present in class. And so if you kind of go through and do the homework and have a reasonable grasp of that, you'll do fine in the class. Okay, so here we go. Okay, I thought we were going. All right. So, how many of you have heard of the scientific method? Anybody hear that? Yeah. People talk about the scientific method all the time. Well, what are we really talking about when we talk about the scientific method? Well, it's really something that you do, whether you consider yourself a scientist or not. You do this on a regular basis. And so let's talk about why that is. Let's talk about some of the basic tenets of it. So when we talk scientific method, what we're talking about is, first of all, we collect some information. So basically you see stuff, okay? You see something that's going on and you think, what does that mean? And that's what we call is formulating a hypothesis. So a hypothesis is a fancy word, to be honest with you, for just saying, I wonder why that's going on, or I wonder why that's working that way, or things like that. For me personally, I don't use the word hypothesis very often. I usually just say, what the heck does that mean? What the heck's going on there? But if you want to be sciencey, you say the word hypothesis. The key to a hypothesis, though, is this next step, is that you test it. And you do some controlled experiments to see really is what you're thinking is correct or not. A hypothesis, without doing some experiments, is really more just kind of like an opinion or an observation. It might be right, might not be right, but you don't really have proof one way or the other. So when you test that hypothesis by doing some controlled experiments, then that allows you to formulate a theory. And a theory is a way of explaining what you're investigating based on the data that you've generated. So you have some confidence in that theory. Another thing about a theory is that you need to go back and repeat some of the experiments to make sure that what you're doing and what your theory is saying is correct. And so it's during that repetition that people will go and they'll change things a little bit as they get more information and more data. A good example of this process are these face masks we're all wearing, okay? If you're like me, I think back to a few months ago when all this started, and what was the guidance from the medical community? Don't need a mask, doesn't do any good, right? That was the initial, and you still hear some people saying that, those masks don't do any good. That was based on their initial hypothesis, is that they looked at the particle size of the virus, and they looked at some things like that and said, you know, these cloth masks, particle size is such, it's probably going to go through, it's probably not going to do a lot of good. Well, as they looked into it more, in other words, started testing their hypothesis, doing some experiments, what they found is that, you know, these aren't N95 masks, like the ones the real medical professionals need, but you know, it's better than nothing and it does help. Okay, it's not perfect, but it's generally a good thing. Did some experiments, allowed them to then formulate their theory about, okay, you do need to have masks on. That does help. Social distancing helps, masks help, all this helps, okay? It's this constant reevaluation of things. And then finally, they repeatedly test that theory. Now you're starting to see information about which type of mask is better than others, and things like that. So once again, that's this, have a hypothesis, testing it via controlled experiments, and then revising what your guidance is. That is the basic fundamental of any science, whether it's chemistry or anything else, is you go through this process of looking at things, thinking about it a little bit, having a hypothesis of here's what I think is going on, but then you have to test it. And it's that testing thing that separates me just giving you my opinion versus giving you something that has some meat behind it. Even once you have that hypothesis and you do your experiments, then that allows you to get that theory, which tells you kind of what you think is going on, and now you have some proof behind it. But you rarely stop there. You continue to test that theory. You continue to kind of challenge the theory to make sure it's okay. And that's one of the things, and this is one reason why it's good that you're in this class, taking a science class, is you start to understand that process. Because everyone gets mad when you read some guidance on some issue, some scientific issue, and then it changes. Don't those people know what they're doing? Well, they don't, because they have to go through this process. They're making their best guesses. I've never known anyone who came up with a hypothesis that they thought was bad. No one does that. Every hypothesis everyone comes up with, they think it's pretty good, because it's based on some observations. Most hypotheses turn out to be false. As you get the data, you see, oh, it's not what I was expecting. It's a little different, it's whatever. But you know, that's the beauty and fun of science, to be honest with you, is you think you know what's going on, you think about it a little bit, you propose something, you test it, and next thing you know, you've iterated enough that you've kind of figured it out. Okay, let's talk about some terms that you'll hear a lot. We've talked about it a little bit, but I just want to go through them again. The first thing is observation. So an observation is just a measurement or something that you see in nature. So you see something going on and you start noticing it and you say, what the heck is that? The hypothesis is that initial attempt to describe really what's the reason for that observation or that measurement, okay? And the experiment would be the means of testing that hypothesis. And the key here are these last two words, controlled observation. Controlled is really the big one there. When you're designing experiments, you try and keep as much constant from experiment to experiment as you can, and just isolate those variables that you're interested in investigating and see what changing those does to your results. So controlled experiment is the thing. If you move on in science and you do a lot of experiments, you always have controls when you do them. And that's so that you don't get a false positive or false negative or something like that. And then finally, theory is if the hypothesis turns out to be pretty good, then you have this tentative. We say tentative because remember, we're going to keep testing it. We have this description of what's going on to explain what we've seen, and that's the theory. The last one here you see is a law. Laws are very uncommon because laws imply, or they don't imply, laws are such that you have a mathematical explanation of it. So, and it works pretty much all the time. And so we'll talk about laws of thermodynamics a little later in the year. That's an example of laws, and there's math around those laws that explain it. You don't get a lot of laws just because of the math component and things like that. You get a lot of hypotheses. You get fewer theories because the hypotheses tend to fall away and prove not to be correct. And then you get even fewer laws because of the math component.
You said tentative. What did you say about tentative? You said when you use that word that
the tentative model for the theory, is that what you're talking about? Yeah, that's because remember when we talked about theories, we said even when we've got a theory that we think is pretty good, we'll continue to kind of push on the theory and stress it, and we'll do some different experiments to see. So that's why I say tentative model, because it can change even if you get to the point of having a theory because you know, and going back to the face mask example, one could be, enough experiments were done to say that having masks on versus not has value. But now you're starting to see it get fine-tuned a little bit, of certain types of masks are a little bit better, they think, than other types of masks. So fundamentally, the theory of masks is still kind of holds up, but it's being tweaked a little bit by, as you do more experiments and get a little more into the details of it. Okay? All right. Okay, so let me ask you a couple of questions here. Which is more likely to be shown to be incorrect, a hypothesis or a theory? Which has the greater chance of being proven wrong? Yeah.
A hypothesis,
Okay, why do you say that?
because it hasn't really been tested, hasn't gone through the experimental phase.
Right. It hasn't gone through the experimental phase. It might be a great idea, but until you start doing some experiments, you don't really know. You know, there's a saying in the lab of, you got to do the experiments. You know, it's nice to think about stuff and you might have great ideas, but boy, you got to do the experiments. Okay. The next question. What reliably predicts the behavior of matter, and what provides an explanation for that? So what predicts it of those things we talked about? Any ideas? Well, the one we said that was really good was what? It was the law, right? So the law, we said, is really good at predicting things because it's even better than the theory. Which of these things provides an explanation for that behavior? Well, that's our friend theory, right? We said hypothesis was our first guess at it, our first opinion on it, our first thoughts on it, however you want to think of that. Then we did some experiments, and then we maybe modified that hypothesis to get to our theory, which we say explains what's going on, and then we continue to test that, and at some point, if we test it, have a mathematical explanation, then we get to the law. So that's kind of the process we use. And that's not a chemistry thing, that's just a science thing, okay? We certainly use that kind of thought flow in chemistry, but we also, you use it pretty much in your everyday life or things like that. The thing I would say is, and this is true whether you're thinking about stuff or you're reading articles or something like that, you always want to ask, how did people get to that hypothesis? And then once they had their hypothesis, did they follow it up with any controlled experiments? Remember, we say controlled is the key there. And then did they use that data from the controlled experiments to get their theory? If they didn't do that process, then it may not be a great theory, hypothesis, whatever. Doesn't mean it's wrong, but it does raise some questions. Okay, let's talk about chemistry a little bit. Chemistry, simplest definition is it's the study of matter and the properties of the matter and the changes that the matter undergo. It's central to our fundamental understanding in many of the scientific fields. So if you think of the textbook, what's the title of the textbook? Chemistry, the Central Science, right? Chemistry has been called the central science for a long time. I don't know where that came from, but the reason is if you think about it, pretty much everything we do, you can explain on a molecular basis, an atomic and molecular basis. And that's what chemistry is doing. It's looking at matter. Matter is pretty much everything, right? You're matter, I'm matter, the desk is matter, the floor is matter, all that stuff is matter. And so chemistry is looking at the properties of it and then the changes that it undergoes. So what would be an example of a property of matter? Any thoughts? What color is my shirt? It's black, right? I have to check, but it's black. That's a property of this matter. The matter is the shirt. A property is that it's black. If I were to had to make this shirt, I'd have to do some type of chemical reaction to make the cloth material, okay? Either a reaction in a plant if it's cotton, reaction in a lab if it's some synthetic material, things like that. So, hi.
I'm so sorry I'm late. I went to the wrong building.
Oh, that's okay. So here's some examples of this. So in medicine, in the medical field, you think of people working on the vaccine for COVID. Well, that's a chemistry type thing. They're looking at of how do we come up with molecules to put into the vaccine that will interact appropriately with the virus to deactivate it. Biochemistry, you see things there. There they have an example of the firefly reaction. Energy with the solar panels, other technology things. It all comes down to some type of chemistry type thing going on. Okay, so why study chemistry? Let's talk about that for a second. So other than the fact that they made you take this class because of whatever your major is, and they said you got to take Gen Chem, what other reason? Does anyone have a reason why they would like to take chemistry class? Yes.
To understand how things work.
Yes, that's a good answer. To understand how things work and to understand it on a really molecular and atomic level, and then kind of scale up from there. So what do chemists do? So there's like a few different types of chemists, just as like if someone was a physician, all the physicians don't do the same thing. All chemists don't do the same thing. There's specialties within that. The first one we'll talk about is making new kinds of matter. So those are synthetic chemists, we call it. And usually they either work on organic molecules, polymer molecules, or inorganic. Organic compounds are ones that contain carbon. That's the simplest definition. If you're an organic chemist, you do reactions with compounds that contain carbon. If you're an inorganic chemist, you do reactions with compounds that don't contain carbon. Pretty simple organic, inorganic difference there. And polymer chemists, those tend to be chemists who work on plastics, so to speak. So any polymer type material, that's the kind of chemistry and reaction chemistry they would be doing. So those are the chemists that make stuff. That's what a lot of people think of when they think of a chemist, mixing stuff together and making some new compound. That's the synthetic guys, makes new kinds of matter. Another one is a measure of properties of matter, analytical and physical. So me personally, my PhD is in analytical chemistry. I fall into this bucket of being interested in measuring the properties of matter. Does anyone watch any of the CSI TV shows? Or do you know what those are? That's analytical chemistry. All that equipment you see in the lab and they're generating the results and all that, that's equipment that we use on a routine basis. I will tell you it's not as easy as they make it look. And the normal people who in the lab don't typically look like those people either. They look more like me. So you can draw whatever conclusion you want from that. It's up to you. So the idea behind the properties of matter is, remember when we talked about the scientific method? It's great to have an idea of what's going on, but you really got to do some experiments to test it. If you don't get good data out of those tests, it's really hard to know if what you're thinking is correct or not. And that's where the measurement stuff comes in. Being able to have good methods and accurate methods is critical to generating the data you need to make decisions. Let's talk about the COVID for instance. So right now, those of us in the room are sitting here, we've got our masks on, which is lovely. We've got a whole bunch of people who are sitting in a Zoom meeting right now. And I would say neither group is 100% happy with the situation. If we had a COVID test that was kind of similar to a breathalyzer test or something like that, where you literally could come to the room, blow into a tube or something, and immediately get a result of you're good or you're not good. And none of us would have to have these masks on, and we'd all be in the room together, right? Would everyone agree with that? So that's an example of, and what do you hear all the time? The tests aren't fast enough. We're getting too many false positives. They're not sensitive enough, things like that. That impacts the ability to manage the social issues associated with COVID is the testing ability. That is true on almost everything you do when you're making decisions and things like that. You want the data, okay? You want the data. What would it be like if you were in this class and you took your first test and you asked me, well, what did I get on the test? I said, oh, you did okay. Would that be very helpful to you? No, you want to know I got a 95 or a 55 or whatever, because then you know, gosh, I'm in pretty good shape, or no, I got to study a lot more or something like that. Once again, it's that data that you get. That's what the analytical and physical chemists do. And then finally, you hear about models all the time, okay? You hear about the COVID models that say we're going to have a spike because it's trending up. We're modeling it, we're predicting. Models allow you to take data that you have, hopefully it's good data, and then through mathematics, project it out into the future of what's going to happen. And modeling is done all the time. The weather maps and that, a lot of that's modeling. That's how they know if it's going to rain Thursday or not, is they look at the projections on the model. There's a saying about models, garbage in, garbage out. So in other words, if you have bad data that goes into the model, it's not going to predict well. So that's why it's very important on this measurement part here to have good data that you're generating so that it goes into the models and those models are good. So that's just a brief thing on what chemists do. And let's go back to matter and just talk a little bit about what we mean with matter. When we talk about matter, it's really a pretty simple definition, in that it's really anything that has mass and takes up space, okay? So basically, matter is stuff. And so in the chemistry world, though, when we think of matter, we think on a little bit more microscopic scale. We think in terms of atoms. And so on the left there, you see atoms of an element and then molecules of an element. Some elements like to form diatomics. In other words, two of the atoms kind of go together. And so that's kind of the difference there, is you have the atoms. And so one way in chemistry that they draw things is these little circles represent atoms. Different colors represent different types of atoms. Then on the right here, we have molecules of a compound. So if you look at that one, you see the green and the blue. They're all the same. So that means they're all the same compound. And a compound, remember, is just something that has two or more different atoms in it. And then finally, a mixture. Here's a mixture of elements and compounds. So we've got some elements there, the ones that are single color, and then we have compounds, the one that has multiple colors. So the matter definition is really pretty simple. And that's what we're going to spend the next semester, this semester and next semester, studying mass, studying elements, studying compounds, mostly compounds. But this is chemistry. This is it. And you thought it was hard. It's not. Very simple. So let's talk about how we classify things. There's two things we talk about. We talk about the state of the matter, and we talk about the composition of the matter. Okay, when we talk about states of matter, there's basically three states of matter: solid, liquid, and gas. Now, in teaching this type of class before, I've had some people want to bring up some more exotic states of matter that are out there. We're not going to worry about those. For this class, we're saying there's three states of matter: solid, liquid, and gas. And in this little picture down here, it gives us what that would be for water. So you see the icebergs, that's the solid state. You see the water, the ocean, or whatever that is, that's the liquid state. And then water vapor that's going up into the air, That's, of course, the gas phase. So states of matter, solid, liquid, and gas. Which one is it? So when we classify things, this is a good scheme to follow to kind of understand how you classify matter. The first question you have to ask yourself, is it uniform throughout? What does uniform mean? The same, yeah. So if you had a big bowl of it and you took some from here or took some from there, whatever, is it the same? If the answer is no, on the left there, we have a heterogeneous mixture. And heterogeneous means it's not the same throughout. If you took some from over here and took some from over on the left, then it would be different if we analyzed it. If it is uniform, then we say it's homogeneous. So then if it's homogeneous, you ask, does it have a variable composition? If it's no, if it doesn't vary, that composition doesn't vary, then you say it's a pure substance. If it's a pure substance, you ask yourself, does it contain more than one kind of atom? If it's just one kind of atom, then that means it's an element, right? We said if all the atoms are the same, that's the definition of an element. If it has more than one kind of atom, we said that 2 or more atoms makes it a compound. So then that would tell us it's a compound. So in each case, it's a pure substance, but one case, it's an element, the other is a compound. Going back up to the does it have a variable composition, if the answer is yes, because remember, we said the whole bowl is homogeneous. If it is, if we have variable composition within that, then that solution, which we'll call a solution, is a homogeneous mixture. So in the last class, I had someone who asked me about that. They said, wait a second, I thought you said homogeneous up there, then you're saying homogeneous again there, but you're saying it has a variable composition. Here's the way to think of this. Let's say I had sugar and water, okay? If I put the sugar and dissolved it in water, the sugar is going to all dissolve, and then in that solution is sugar water. So anywhere I pick out of that solution and analyze it, it'll have sugar and water in it, right? So that tells me it's homogeneous. The mixture is homogeneous throughout. But that homogeneous, does it have variable composition? It does, because it's not just sugar molecules and not just water molecules. It's sugar and water molecules. So that's that. Does it have variable composition? Yes, homogeneous mixture. That's how you get to that. Those are usually solutions. The other side on pure substance would be if I just had the sugar by itself in a bowl. That's going to be a pure substance, contains more than one kind of atom, and it brings us down to compound. So do you get the difference there on the different homogeneous kind of steps? Okay. Let's talk about classification of matter and substances. So a substance has distinct properties and a composition that does not vary from sample to sample. So there's 2 types of substances, elements and compounds. An element is just the simplest form we can get. So in other words, you can't decompose it to anything simpler. So if you have, a carbon atom by itself, you can't do anything to that to make it something less. But if you have that sugar molecule, which has carbon, hydrogen, and oxygen in it, you can do things to that to change that composition. And so a compound then is a substance which can be decomposed, reacted, however you want to think about it, to some other simpler substance because it's made up of more than one element. So in the sugar example that has carbon, hydrogen, oxygen in a sugar molecule, so you can do some reactions and break that down to other compounds, and you can break it down further to carbon, hydrogen, oxygen, things like that. So the big difference here, elements can't be broken down. That's the simplest it gets. compounds can be broken down. When we talk about classifying matter based on composition, a couple things I want to talk about. First, there's some examples of molecules on here. So once again, this is one of the ways, there's a bunch of ways, but this is one of the ways people will draw molecules. Each of the balls represents a different atom. You see the white one's hydrogen, the red one's oxygen, the kind of blackish grayish one is carbon. And then the way they're stuck together, that's the bonding together, and then that's the shape that the molecule would have. We'll talk about all that more later in the semester of bonding and angles and all that fun stuff. But that just tells you in general that you can see, like oxygen, for instance, is two oxygen atoms stuck together. You get to water, you have oxygen with the two hydrogens on it, and then so on with the others. Ethanol, you start having some carbon, you have a couple carbons there, and on down the line. Atoms are what is kind of the building block of it. You don't see it as much anymore, but when I was your age, everybody had to buy a little kit, a little molecule kit. You'd build the molecules, almost like Tinker Toys type thing. You guys probably don't know what Tinker Toys are either. Legos, let's go with Legos, something like that. You don't see that much anymore, but they do all the computer screens. But in the old days, that's what you did. Each element is a unique atom. And so each of those atoms, each of those elements has distinctive properties. And we'll learn about those in the class, and we'll learn about it in the lab as well. A compound, once again, I'm going to say this again, is made up of atoms from two or more different elements. So you start getting to, like you see the structure for aspirin there. You see there's a bunch of carbons. There's oxygen, there's hydrogen. That's taking those atoms to build the molecule, and then that aspirin molecule will have some properties that are unique to that configuration of those atoms. Let's talk about the elements for a second here. Currently, there are 118 elements in the periodic table. We'll look at the periodic table in a moment. 118, that's a lot. If you look at the Earth's crust, and so the Earth's crust is basically the dirt, right? 90% of it is made of 5 elements. We have oxygen, silicon, aluminum, iron, calcium, and then others account for about 9%. Isn't that amazing? There's 118 elements out there, and 90% of it is one of these 5 elements. Question for you. Is anyone surprised by how much silicon is there? Where do you find silicon? I bet most of you, or at least a lot of you, have walked on silicon before. Pardon?
We walked on it?
You've walked on it, and you thought it was good. How many of you have been to a beach? Anybody been to a beach? Sand is silicon. There's silicon in sand. That's why you see that number so high, because you think of all the beaches, you think of the floors of the oceans, et cetera, et cetera. There's silicon in there in the sand. In your body, 90% of your body by mass, oxygen, carbon, hydrogen. Others about 7%. Pretty interesting. What do we see from this? Oxygen is kind of important. It's important in our bodies. It's important in the earth. It's an important thing. So even though there's a lot of elements, there are some that are a little more dominant than others. Okay, so how do we talk about these elements? I mentioned the periodic table a little bit, and we'll look at that a little more closely. But let's talk about how we communicate about atoms. And all the elements have a symbol, okay? And here's a list of some of them. So you see carbon is C, fluorine is F, hydrogen is H, iodine's I. Great, this is really easy to remember these. Carbon begins with C, is C. Fluorine begins with F, is F. Great, those are good. We're gonna really know those well. Well, we get over here, When we look at copper, copper's Cu. How come that's not Co? Irons, Fe. Where the heck did that come from? Leads, Pb, mercury, Hg. Well, what you see is on the side here, it says where it comes from. And a lot of this is from Greek names or Latin names. Usually it's Latin, but other language names. And that's where it comes. That's why those, carbon, perfect sense. The big C. Iron, Fe. Where the heck did that come from? Well, it came from this other language. So here's what I'll tell you right now. You got to just memorize this stuff. There's no way around it. The ones like carbon and that's pretty easy, pretty self-explanatory. The other ones, you just got to spend some time and memorize them. These are the symbols that we use as chemists to express reactions, compounds, things like that. The other thing is, if it's a single letter, that letter will be capitalized. If it's two letters, like calcium, aluminum, bromine, that kind of column, you see the first letter is capitalized, the second letter is not. So if you capitalize them both, it's incorrect. Okay, that'll get marked wrong. Because then you're expressing something different in the chemistry world. So it can be a single letter like that first column. It could be two letters, a capital and a small like the second. And then the third column are some examples of ones that on the surface don't seem like it makes any sense where the symbol came from. So please memorize the elements and symbols. I'll show you in a minute the ones to focus on. I'm not expecting you to remember 100 and something of them. Because if you did that, then you would know more than me, and I'd be embarrassed. Okay, periodic table. How many of you seen a periodic table before? Yeah, how many of you love the periodic table? Don't be shy. Yeah, there we go. There we go. We got a couple of them. I have a pair of periodic table socks. Maybe I'll wear them one class. We'll see. We'll see how it goes. So periodic table. You talk about it in terms of columns. So you see the 1A, 2A, 3B on down the line, and 3A over here. You talk about columns. We talk about rows. So the rows would be 1, 2, 3, 4, 5, etc. on the left there. And the periodic table is set up in a way that, as we'll learn, different rows have different properties, different columns have different properties, and the element's location on the periodic table tells us some things about properties of that element. Reactivity, things like that, electronegativity, words like that you'll be just rolling off your tongue before the semester is over. So what's important to memorize is the first 5 rows, okay? You need to know all those, so the first 54 elements, definitely know those. And then when you get to this 6th row, look at the ones that you go, oh, I think I've heard of that, then you should know those. So what are some examples of that? Lead at 82, everyone's heard of lead. Mercury at 80, gold at 79, platinum 78. Tungsten 74, you may not have heard of that, you might have, but the main reason you got to memorize it is it's W, and my name's Walter, so I like that one, so you got to know that one. But some of these others, radon is one you may know, because if you ever buy a house or something, you got to get radon testing and that. But astenine, I've never even heard of that. Never known anyone who's ever done anything. So the ones like that, those kind of oddballs, these down here, we're not going to worry about at all. But those first ones up there, you need to know. Does anyone know what, you see the stair-step dark line there? Does anyone know what that means?
Metalloids.
It means metalloids for the ones who are touching it. But what it also means is everything to the left is metal and everything to the right is non-metal. So the ones, as he said, the ones that are kind of touching, we call metalloids, which just means they kind of behave like metals, kind of behave like non-metals. But what you see, though, on the periodic table, which I always think is interesting, is a lot more elements are metals than non-metals. Yet, I mentioned organic chemists out there. Really, organic chemists pretty much work with carbon, nitrogen, oxygen, hydrogen, and a few of the halogens. So most reaction chemistry is up on these nonmetals. That's where most of the action is. Not totally, but most of it. So periodic table, we'll talk more about this as the class goes on, but this is just kind of your first look at it in this class. Okay, let's talk about compounds and composition. So here we're going back to water. They're telling us hydrogen's the white one, oxygen's the red one. There's what the molecule looks like. And compounds have, so a water molecule always has 2 hydrogens and 1 oxygen. It's always H2O. So whether you get the water out of the drinking fountain down the hall or at home or out of the river or wherever, if it's water, it's H2O. And it's not H3O, it's not H2O2. If you have those, that's something else. And so what this means is that this definite composition is actually a law of constant composition, or the law of definite proportions. So what that means is, someone went through that whole scientific method on this stuff, right? And they got it to the point of where they could do some math and prove that it's always this way. And so this is one of the times when something does have a law that governs it. So if I tell you something's water, doesn't matter if it's frozen, doesn't matter if it's liquid, doesn't matter if it's a vapor, it's H2O. If it's not H2O, it's not water. And that's this law of constant composition, or law of definite proportions. Okay. Let's talk about, once again, with the classification of matter, let's look at mixtures for a second. So mixtures exhibit the properties of the substances that make them up. So going back to the sugar water example, that'd be a mixture. You took some sugar, you dissolved it in water. So that solution of sugar water is going to have different properties of water by itself or a bowl of sugar, right? And those new properties are going to take into account some of the properties associated with water and some of the properties associated with the sugar molecule. So if the mixture varies in composition throughout a sample, it's heterogeneous. If it has the same composition through the sample, it's homogeneous. A homogeneous mixture is also called a solution. Now, if you're like me, when I hear the word solution, I assume it's a liquid. And most of the time, that's true. But in chemistry, by definition, if it's homogeneous, it could also be a homogeneous solid, a homogeneous gas, in addition to a liquid. So just kind of remember that technically, solids and gases can be called mixtures, or can be called solutions as well when we're talking about homogeneous mixtures. Usually though, you're talking about solutions, liquid solutions, but the others are true as well. Okay. So when we talk about properties of matter, we talk about physical properties and we talk about chemical properties. So let's talk about those two things for a little bit now. Okay, so physical properties are observed without changing the substance into another substance. So in other words, we can watch water change physical properties, but the water doesn't change. We didn't do anything to the water. We didn't decompose the water. Some examples are color, odor, density, melting point, boiling point, hardness. Those are all things that are unique to the substance, but when you do that evaluation of those things, you haven't degraded or harmed or changed this substance. I'm not going to talk about this condenser slide. I'll talk about that a little bit later. Instead, I'm going to go to chemical properties. And chemical properties are observed, can only be observed when a substance is changed into another substance. In chemistry, we call a chemical change a chemical reaction. So in general, no one goes around saying, oh, I'm doing chemical changes. You say, I'm doing reactions. Okay. Usually don't even say chemical reactions, you just say reactions. And, you know, think about it, just even in your personal life. If I say something to you, like what I just said, chemical properties, I didn't get much of a reaction. If I said, I'm just going to give you all A's for the semester, and we're just going to go home, I think I'd get a bigger reaction, don't you think? So it's that reaction is the chemical change we're looking for. By the way, I'm not doing that, so good thing you didn't react. One common chemical property you hear about is flammable. You hear about something is flammable. Flammable just means it'll burn. So if you have oxygen present, you have ignition source, it'll burn. And when things burn, they always change. There's always a decomposition reaction going on. Okay, here. Tell me if these are physical or chemical changes. If a plant makes sugar from carbon dioxide and water, is that a chemical or physical change? Chemical, right, because you've taken carbon dioxide and sugar, so CO2 and H2O, and you made a sugar compound. How about water vapor in the air forms frost? So a month or so from now, you get up, you go out the door in the morning, and you see some frost on the ground. Is that a chemical change or a physical change? Physical, right. The water's still the water. Just went from being in the vapor, and now it's a solid on the ground. Goldsmith melts a nugget of gold. So you got a chunk of gold, you melt it, and now you pull it out, make it into a nice gold wire. Is that a chemical change or physical change? It's a physical change. It's still gold. And remember, we also talked about with gold, gold's one of the elements. Elements don't do anything, right? You can change that physical, but you don't change the chemical of them, because that's the basic thing. Okay, types of properties. There's two types of properties we talk about. Intensive properties and extensive properties. And so it's important to remember the difference. I'll tell you a little trick to remember the difference. So intensive properties are independent of the amount of the substance that is present. So whether you have a small amount or you have a truckload, these properties will be the same. And a way to remember intensive properties, intensive begins with I, independent begins with I, and then finally it says these are often used to identify substances. That begins with an I. So the I's all go together. That's how you can remember intensive. Some examples are density, boiling point color. Who knows what density is? Anybody know what density is?
How much of it?
Pardon?
How much of it?
Sort of. So density, and we'll do this in, I think, one of the first couple of labs. Density is the mass of something per volume. So it's kind of like if you had one bottle of something, and depending upon what's in that bottle, the volume's the same, but it may weigh more, it may be more dense, more mass. So density is that. So density doesn't change. A compound has the same density whether it's a little bit or a lot. Extensive properties, well, those depend on how much stuff you have. Total mass is one, total volume. Energy is the interesting one. So if you think about it, just think about food, for instance. If you eat a little bit of food, you have a certain number of calories, a certain amount of energy you can get out of that. If you're going to go run a marathon or something, you're going to need more energy, more calories. You got to put more stuff in to have the energy to do that. So energy is mass dependent, is amount dependent. So extensive properties depend on the amount of the substance. Intensive properties are independent. Okay, any questions? Any questions from the Zoom crowd? Okay. Yeah.
I don't know if you said this when I was in here, but is this going to be online?
Yes, so all the slides are on Canvas. If you go into the files folder, there's a lecture folder in there and all the slides are there. And the goal is to have at least either this lecture or the earlier one recorded and posted in a YouTube thing, but I gotta see if this worked today or not before I let you know about that. Okay, physical changes and chemical changes. So physical changes, we've talked about this a little bit already. Matter changes, but the composition of the substance doesn't. So going back to that water example, you can take water, it's a liquid, you can freeze it, make it a solid, you can heat it up so it becomes a vapor, but it's still water. You just change the form of it, you change the physical nature of it. Chemical changes result in new substances. Examples are combustion, oxidation, decomposition, all that kind of stuff. So those are classes of reactions that you do. What they have in common is if you take something and you do the reaction to it, and you analyze what you started with and analyze what you ended up with, it'd be different compounds, different substances. And so that's a chemical change. And when we call those chemical changes, we call those reactions. Once again, this is that water example. I'm not going to go through that because we've talked about that, but that's kind of the classic example of a physical change. Okay, chemical reaction here, what they've done is they've taken a penny, which has a bunch of copper in it, and they put it in nitric acid. And so they get a chemical reaction. The nitric acid reacts with the copper, and you form copper nitrate, which is the blue solution. It's a little hard to see on the bottom, but it is a bluish solution. And then you get the orangish gas coming off. That's nitrogen dioxide. So the copper and the nitric acid, you've changed the nitric acid. You haven't degraded the copper, but you have changed the form of it, the oxidation state. And don't worry about oxidation state for now, that'll come later. But that then allows it to form this compound, this copper nitrate compound. And then also you get nitrogen dioxide going off. So one thing that happens sometimes, not all the time, but often in the chemical reaction, you can see a color change like this. So you went from a clear solution to a blue solution, and now you got this colored gas coming off. That tells you something's going on. And that usually is a pretty good indicator that a chemical change has occurred. It's not a physical change. You don't always get color changes, but you know, sometimes you do. And those are the ones they always use as examples. Let's talk about separating mixtures. So I mentioned before, my degree was in analytical chemistry. Kind of the specialization was chromatography, which chromatography is a fancy word for separating things. So I like to separate things. It's fun. There's some different ways you can do separations: filtration, distillation, chromatography. And in the lab this semester, you'll do filtrations. Distillation you'll do if you take organic chemistry in a year or two. Chromatography, if you take my instrumental class, we do that. We do chromatography in there. But let's just talk about those briefly. So filtration, all you're doing is removing solids from liquids. Does anybody ever make spaghetti? Okay, what do? You put the noodle, you boil water, you put the noodles in the water, you cook them for however long, and then what do? You strain them. You just did a filtration. Okay, that strainer was your filter. You poured the noodles and the water through there. The noodles stayed in the strainer, right? The water went through. You've just done a filtration. That's what they're doing here. Obviously, it's not spaghetti, but it's the same idea. Is that filtration is simply a way to remove solids out of a solution. Okay, I told you I'd talk about the distillation a little bit later. Here we are. So distillation is a process where you use different boiling points of things to separate them. So boiling point basically is the temperature at which a compound will volatilize And different compounds have different boiling points. By heating them up and then collecting them, you can separate things that way. And this is a distillation apparatus. And so basically how this works, just kind of walk you through this. On the left-hand side, you see on the bottom there, a Bunsen burner. So that's a heat source. They have what they say is salt water. So sodium chloride and water in there. Sodium chloride isn't very volatile. Water is more volatile. So as you heat it up, the water vaporizes. It goes up that tube. This thing they have labeled the condenser is a long tube that has a tube within it. And the outer portion of the tube, you run cool water around, and then the vapor goes in that middle tube. As the vapor hits inside that middle tube, the cooler water on the outside cools that inside of the tube and lowers the temperature below the boiling point again, and it drops out, and then now the water drips in, a few drips there, and the idea is that that water on the back end of this receiving flask won't have any of the salt, because the salt isn't boiling off at the temperature that you're operating at, just the water is. So this is a simple way to purify salt water, for instance. So the key, though, is you're doing a separation and you're taking advantage of what you know about the properties of the things that you're trying to separate. In this case, boiling point. Would boiling point be different if that was a much bigger flask? Is boiling point intensive? It is, it's intensive, and that means it's independent. So whether that flask is 10 mils, 100 mils, whatever, the boiling point doesn't change. Now, the amount of energy we have to get into it to get to that boiling point would change, right? Because we talked about putting energy in, and that with that flame, what you're doing is you're putting energy into that. Okay, I'm going to save chromatography till the next time, Wednesday, because I love chromatography and I don't want to rush. And this will give you a little bit of time to wipe down your desk, please. And then you guys will be Zooming on Wednesday, and we'll have the Zoomers come in on Wednesday to be in person. So thank you. If anyone has any questions, please let me know. If anyone online has a question, please let me know. Otherwise, that will be the end. Okay. Thank you.